Hello everyone, welcome you all at Lokesh Sir Unlimited Study Zones. So, in the topic dual nature and radiation, we studying the topic laws of photoelectric emission. So, we have seen the various experiment, various observation performed by the Leonard, and we conclude that during the photoelectric effect, a photoelectric current is flowing through the external circuit. Now, what are the important laws related to the photoelectric emissions? So, these are called laws of photoelectric emissions. First law, for a given metal and frequency of incident radiation, the number of photoelectron ejected per second is directly proportional to the intensity of the incident light. Yes, we already have discussed about this that number of photoelectrons that is proportional to the photoelectric current is directly proportional to the intensity, means the emitted electron depending on the intensity of the light, because there is one to one correspondence between the light ray incident radiation and the number of electrons. Okay, so number of photoelectrons ejected, or you can say photoelectric current, is directly proportional to the intensity of the incident light. As you increase the intensity, number of photoelectron will be increased, so the photocurrent will also increases. Second, for a given metal, there exists a certain minimum frequency of the incident radiation below which no emission of the photoelectrons takes place. This frequency is called threshold frequency. As we know, the work function, the minimum energy to fetch out the electron is equals to h nu naught. Okay, so for a minimum energy, there should be a minimum frequency because h is constant. Clear or not? Like minimum energy is 30 electron volt and h is like 3, so nu naught should have either 10 or more than 10, then only this multiplication will result at least 30 electron volt. Clear? So there is minimum frequency. Okay, beyond that the electron can be fetched out of the surface. So for a given metal, there exists a minimum frequency of the incident radiation below which no emission of the photoelectron takes place. This frequency is called threshold frequency and denoted by nu naught. Clear? An energy corresponding to this frequency is called work function, and this is given by h nu naught. Above the threshold frequency, the maximum kinetic energy of the emitted photoelectron is independent of the intensity of the incident light but depends upon the frequency of the incident light. Yes, yesterday I shown you that if there is total energy of the radiation is E. This energy is contributed in two parts. First, to supply the energy as a work function to remove the electron from out of surface, and remaining energy is contributed as the kinetic energy, maximum kinetic energy used by the fetched out electron. Clear? So here, as this is constant, so if you make it this side half mv square, so this becomes equals to h minus pi naught. Okay, means the difference that is depending on the total energy. Okay, above the threshold, and total energy of the radiation is equals to half mv square equals to h nu minus phi naught. Clear or not? So as you increase the value of the frequency of the incident radiation, there will be more advantage for maximum kinetic energy. Means on increasing frequency, kinetic energy also increasing. Clear? Yes. So above the threshold frequency, the maximum kinetic energy of the emitted photoelectron is independent of the intensity. Yes. So this energy depending on the frequency of the radiation, not on the intensity of the radiation, because energy is related to the frequency only. Clear incident, but depends on the frequency of the incident light. The photoelectric emission is an instantaneous process, means just incident light impacted on the surface uh, only at that point without any time lag. Okay, this time lag is very small, near about 10 to the power minus 9 second, 1 nanosecond. Okay, so this is called spontaneous emission. The photoelectron emission is instantaneous, only that instant process, no time lag. This time lag between the incidence of radiation and the emission of photoelectron is very small. This is less than that less than even 10 to the power minus 9 second. Then, so these are the laws of photoelectric emission. Again, repeating the first point for the laws of photoelectric emission, for a given metal and a frequency of incident radiation, the number of photoelectrons ejected per second is directly proportional to the intensity of incident light. Yes. Yesterday we seen that the number of photoelectrons ejected depends upon the number of radiations. Okay. And the number of radiations per unit time per unit second. What is intensity? Intensity of radiation is equals to number of radiations per unit time per second per area per unit area. Clear? So as you increase the number of radiation in a unit area in a unit second, means in the place of 3, if you have taken 5 radiations, okay, this means there will be exposure for 5 electrons, right? So there may be chance that 5 electron may be ejected out of the surface. So what you have done, you have increased the intensity. On by increasing the intensity, incidented radiation increases, so the fetched electron, number of fetched electron also increases. Clear or not? Yes, done. Okay, next question. Yesterday we have seen the concept that maximum kinetic energy half mv square is equal to ev naught. Yes or no? Yes. The maximum kinetic energy is controlled by ev naught. Okay. So the question related here with this concept, the stopping potential of an experiment in photoelectric effect is 2 volt. Okay. So V naught is given here 2 volt. What is the maximum kinetic energy of the photoelectrons emitted? Okay. So what is maximum kinetic energy? So as I said, for a photoelectron, the maximum kinetic energy is given by half mv square. This is called Ke max. For an electron, what is charge? Charge equals to E. Now, stopping potential is equals to given is 2 volt. Okay. So, the energy is equals to 2 into E. So, the charge of E is, so it is equals to 2 electron volt. Okay. So, the energy equals to how much? It is equals to 2 electron volt. Because E, the unit of E is equals to Coulomb. The unit of E is equals to 1.6 into 10 to the power minus 9 Coulomb, multiplied by 2 volt. Yes, if you have put the value of electron in the form of charge, then you will have your answer in the form of joule. So here the energy will be about the form of, so 16 to the 32. So it will be equals to 3.2 into 10 power minus 19. Sorry, minus 19 joule. But if you have taken electron as E, then your energy equals to 2 electron volt. Clear? Yes, because electron has potentialized by a potential of 2 volt. So in the form of electron volt, your energy equals to 2 electron volt. Clear? Hmm. Next question. Show graphically how the maximum kinetic energy of a photoelectrons emitted for a photosensitive surface varies with the frequency of the incident radiation. Show graphically how the maximum kinetic energy. Student, yesterday we have studied about this. This maximum kinetic energy, EV naught, equals to h nu minus h naught. Half mv square equals to h nu minus h naught. Okay. Let us again derive this relation. Yes. So what we have during the photoelectric effect, if I incidented a radiation energy of E, this contributed in two parts, h phi naught plus half mv square. Clear? So half mv square is kinetic energy. This is maximum kinetic energy. And this is equals to h nu equals to phi naught. This is a constant value plus half mv square. This is kinetic energy. Okay. So here we have to make the graph between. This is called maximum kinetic energy. In the place of this, you can write K max. Phi naught plus K max. Now you have to draw the graph between the frequency and K max. Okay. So K max equals to K max equals to h nu minus phi naught. Okay, h nu minus phi naught. This is the value of maximum kinetic energy. So you see, by increasing, as this is constant, so by increasing the value of incident radiation, if you're increasing the value of incident radiation, then K max, maximum kinetic energy, also increases. Clear or no? Yes. So draw the graph here between kinetic energy maximum. Yes. For a given metallic surface, suppose there is a work function for the first metallic surface equals to nu naught. Now, by increasing the frequency, by increasing the incident frequency, kinetic energy also increases. Clear or not? For second material, so for second metal, the threshold frequency for the second metal equals to nu naught dash. So by increasing the frequency, its kinetic energy for the fetched electron also increases. Clear or no? Yes. Now, see here, this is what intercept. Okay, intercept you will get when frequency becomes zero. Check here. When incident radiation frequency equals to zero, nu equals to zero. If you putting here nu equals to zero, then K max equals to minus of phi naught. Clear or not clear? Means this is equals to work function. Work function. So check here. This is for the zero frequency. For a zero frequency, the value of kinetic energy becomes phi naught 1, first work function. For kinetic energy 0, this is equals to phi naught 2. Clear? Yes. If you put here nu equals to 0, you will have kinetic energy equals to phi naught. Clear? So for two metals, there are two phi naught 1 and phi naught 2. Done this question. Now, next question. The figure shows a plot of three curves A, B, C showing the variation of photoelectric current versus collector plate potential for the different intensities I1, I2, I3 having frequencies nu1, nu2, nu3 respectively incident on a photosensitive plate. Point the two curves for which incident radiation have the same frequency but different intensity. Okay. So you have to point the two curves for that incident radiation has the same frequency, okay, but the different intensity. Okay, so it is obvious for B and A, they have the same frequency because they have equal cutoff potential or stopping potential. As you know, key stopping potential is depending on the incident frequency, and for a same frequency, radiations of same frequency, you will have the same stopping potential. Yesterday already we have derived this one with the formula. Yes, check here. E V naught equals to H naught up H nu upon E minus phi naught upon E. So if you increase the frequency, then your stopping potential also increases. So for a same frequency radiation, there will be a same stopping potential. So these two signals, I2 and I3, intensity of radiations I2 and I3, they having same frequency, incident frequency. So if the first one having incident frequency nu, second one also having frequency nu. Clear? Yeah, they may have the different intensity, but they having the same frequency. Yes. The photoelectric current is directly proportional to the intensity of incident radiation. Energy of the photoelectrons or cutoff potential depend on the incident's radiation. But see here, energy of photoelectrons or cutoff potential depends on incident radiation. What? Energy of photoelectrons or cutoff potential depends on the incident radiation frequency. Yes, energy and cutoff potential depending on the frequency. Curve A and B have got the same cutoff potential. For these two curve frequencies will be same. Yes, what I said, they having the same frequency because they having same cutoff potential. Clear or not clear? Yes, but here for the radiation 1, cutoff potential is more negative. Means this is more kinetic energy. This radiation having more kinetic energy. So we have to apply the more negative potential. It means here the incident frequency like nu dash will be higher than the nu. So for this radiation, nu dash will be greater than nu. Clear? Yes, done. Okay, starting our next topic, Einstein photoelectric equation. According to the Planck quantum theory, the light consists of tiny packet of energy called quanta. One quanta of light radiation is called a photon, which travels with the speed of light, and energy of the photon. We have studied earlier that it is given by E equals to h nu. Okay, so like light is coming in the form of photon, and this one packet of energy is called quanta. Okay, so it is quanta of light is called photon. Okay, quantum of light radiation means different signals having different packet of energy. For a context of light, the packet of energy, the quantum of light radiation is called a photon. Okay, so, yes. So energy of the photon, one photon is given by E equals to h nu, where h is Planck constant, nu is the frequency of incident radiation. Einstein assumed that the one photoelectron is ejected from a metal surface if one photon. Einstein assumed that one photoelectron is ejected from a metal surface that if one photon of suitable light fall on it. Okay. So when you will have a ejection of one electron, when there is a incident of one photon. Clear or not? So there is a ejection of one photoelectron from the surface on a striking of one photon of suitable surface by one photon of suitable light radiation fall on it. When a photon of light of frequency nu incident on a photosensitive metal surface, the energy of the photon h nu is spent in two ways. It means the total energy incidented at a point of strike equals to h nu. This is total energy E. Now this total energy E equals to h nu is spent in two ways. First, a part of photon energy is used to free the electron from the metal surface, which is equal to the work surface of the function phi naught of the metal. So first part of some part of energy is used as a work function to just to release the photoelectron from the attraction of this metallic surface. Okay, and fetching it out just out of the surface. This is called work function. This energy required is called work function of the metal. Clear? The rest of the energy of the photon is used in giving the maximum kinetic energy K max to the emitted photoelectron. The rest of the energy is utilized by the electron as its maximum kinetic energy. Clear? So here h nu becomes phi naught equals to h nu naught plus half mv square. Clear? Yes. So kinetic energy K max equals to half mv square. So by the equation h nu equals to phi naught plus half mv square. Now derive the relation for kinetic energy maximum. This half mv square, if you separate it out this side, so half mv max square, that is maximum kinetic energy, equals to h nu minus h nu naught. Clear or not? Means K max becomes equals to total energy minus work function, h nu minus h nu naught. Clear, students? So h nu minus phi naught. This equation is called Einstein's photoelectric equation. Also phi naught equals to h nu naught. So we know phi naught is a work function, and work function is the energy to release the electron. So this is the minimum amount of frequency, okay, that will constitute our work function. This frequency is called threshold frequency. So K max equals to E naught minus phi naught, and we seen that K max equals to E equals to h nu and phi naught equals to h nu naught. So taking h as a common, here it will be nu minus nu naught. So K max equals to nu minus nu naught, right? Okay. And the value of K max equals to half mv max square equals to h times nu minus nu naught. So this is called photoelectric equation. K max equals to h nu minus nu naught. Relation between cutoff potential, frequency of incident photon, and threshold frequency. So three things are there. Relation between cutoff potential, frequency of incident radiation, incident photon, means one side here it is V naught that is cutoff potential or stopping potential. Then here it is new original frequency and threshold frequency equals to nu naught. So we have to derive the relation between all these three. So let us see how can we derive this relation. As we know, total intensity E, total energy E is spent in two form, that is phi naught plus half mv square. Clear? And what is stopping potential? Stopping potential is the potential that is used to this suppress this energy, okay, control this energy. Means in the place of E you can write h nu, here h nu naught, and here it is equals to half mv square. In the place of half mv square, this energy, kinetic energy, okay, kinetic energy is suppressed by the electrostatic potential energy ev naught. So the maximum potential negative potential that you applied to control this kinetic energy, okay, is called potential energy ev naught. So this energy is equals to ev naught. Clear? Okay, so this is ev naught. Now ev naught equals to E V naught equals to h nu minus h nu naught. Okay, E V naught equals to h nu minus h naught. So V naught is stopping potential equals to h upon E nu minus h upon E nu naught. Okay, h upon E minus h upon nu naught. Yes, so this is the formula. E V naught equals to h inside the bracket nu minus nu naught. From here you can check EV naught equals to H inside the bracket nu minus nu naught. Got it? Yes. Now, what is the formula for nu? As we know, C equals to nu lambda. So, nu equals to C upon lambda. C is the speed of light. Okay. So, you can place here V naught equals to H upon E. In the place of nu, you can write here C upon lambda. Hmm. Otherwise, yes, from here, let's take equation from here. EV naught equals to H. Now, in the place of nu, there will be C upon lambda. And for a minimum threshold frequency, there will be maximum wavelength C upon lambda naught. This is called threshold wavelength. Corresponding to threshold frequency, the wavelength of the radiation will be threshold wavelength. Yes or no? Threshold wavelength. So this is the relation between the incident wavelength, threshold wavelength, and the stopping potential. Yes. So this becomes the all the relations are here. Fine. Now next question. Ultraviolet radiation of different frequencies, nu1 and nu2, are incident on the two photosensitive material having work function W1 and W2 respectively. The kinetic energy of the emitted electron is same in both the cases. Which one of the two radiation will have higher frequency? Which one of the two radiation will have higher frequency? Okay. So given the kinetic energy for both the electrons is same for both the cases. Okay. So kinetic energy for the electron K max we know is equals to h nu minus work function. H nu minus work function. So it is given here kinetic energy for the first radiation equal to kinetic energy for the second radiation. So h nu 1 minus W1 equal to h nu 2 minus W2. Clear? Yes. So these two are equal. Yes. H nu 1 minus W1 equals to h nu 2 minus W2. Check here. H nu 1 minus W1 or phi 1 work function equals to phi 1. Kinetic energy for the first electron equals to h nu 2 minus phi 2 kinetic energy for the second electron. Clear? What new one? Work is work function. That is work function. But we have here it is taken as W1, but earlier we have considered at phi. Okay. So h nu 1 minus phi 1 equals to h nu 2 minus phi 2. Now check the question. Work in a work function W1 is greater than W2. Here it is given W1 is greater than W2. So W1 greater than W2 means in our sense phi 1 is greater than phi 2. Clear students? So if you taking phi 1 here, this is become plus phi 1 minus phi 2 equals to h nu 1 minus h nu 2. It is given that phi 1 minus phi 2, as phi 1 is greater than phi 2, means phi 1 minus phi 2 will be greater than 0. Yes or no? Phi 1 minus phi 2 equals to is greater than 0. So therefore h nu 1 minus h nu 2 also greater than 0. So h nu 1 is greater than h nu 2. So h and h cancel. So the incident frequency of radiation will be greater than the radiation 2. Clear or not? So nu 1 will be greater than nu 2. Okay. Taking next question, students. The following graph shows the variation of the stopping potential V naught with the frequency nu of the incident radiation for the two sensitive metal X and Y. Where is the graph? Okay, this is the graph. So stopping potential, this is first threshold frequency, and this is second threshold frequency. Stopping potential versus what? Stopping potential versus frequency. Yes. So here it is the frequency. Clear? X and Y. Two metals are there, X and Y. Clearly, X having the less threshold frequency and Y having the more threshold frequency. Okay. Hmm. Which of the given metal has larger threshold wavelength? Yes, check here it is for wavelength. So we know C equals to nu lambda. If threshold frequency increases, then threshold wavelength will be decreases to make this value constant. Yes or no? So for a smaller frequency, there will be larger wavelength. So which you are having a smaller frequency? This one. This one having a smaller threshold frequency. So this one having larger threshold wavelength. So answer, material X having larger threshold wavelength. Okay. So from the graph, threshold frequency for the first material is this one. Second is this one. As frequency of radiation Y is greater than frequency of radiation X, and we know wavelength is inversely proportional to the frequency. So for radiation X, wavelength will be maximum because the frequency is lesser here. So the wavelength will be maximum. Clear or not? So lambda X is greater than lambda Y. Clear? Explain giving reason which metal give out electrons having larger kinetic energy for the same wavelength of the incident radiation. Okay. So you when you have incidented a radiation, two radiations here and here of same frequency, means you having equal energy or equal radiation energy. The work function here is less. So the energy, the rest energy will be more. Means kinetic energy for radiation X will be greater than kinetic energy for radiation Y, because the less energy as a work function imparted here, and here the more energy imparted as a work function. Clear? Yes. Check here. Here nu naught is higher for the metal Y for a given wavelength frequency nu. Kinetic energy for the metal X is greater than metal Y. Clear or not clear? Because work function is more for this one material. Clear or not? Yes. Like you have incidented a radiation of 10 electron volt here. Okay, 10 electron volt and 10 electron volt. For both the situation, you have incidented radiation of 10 electron volt. So here the frequency is less, so less energy consumed as a work function, and here more energy consumed as a work function. Yes or no? So the rest of the kinetic energy will be more for the radiation X. Done? Okay, students. Next, coming to the question number C. If the distance between the light sources of metal X is halved, how will be the kinetic energy for electrons emitted it change? Yes. If the distance between the light source and metal X is halved, means previously there is a metal like this is a metal X. Now distance, previously distance is something like Y kilometer or say X, not X, we have taken surface. So suppose it is A kilometer. And now we have reduced it is up to a by 2. Question is this, what is the effect on the, if the distance between the light sources and metal X is half, how will be the kinetic energy of the electrons emitted from it changes? Okay. So see, by reducing the distance, there is no impact on the frequency because frequency is the characteristics of the source. Previously, there the frequency equals to h nu, and now also the frequency equals to h nu. There is no impact at all on the frequency. Clear? Means no impact all at all on the frequency. It means as there is no impact on the frequency, so no change in frequency takes place. So there is halved. How will the kinetic energy? Yes, no change in the kinetic energy. By distances, there is no effect of kinetic energy. Let us see. No effect because the kinetic energy depends on the frequency of incident light. Yes. Kinetic energy only depending on the frequency of incident light. Clear? Kinetic energy is the function of frequency. It does not depend on intensity. Okay. Next question, students. Radiation of frequency 10 to the power 15 Hz are incident on the two photosensitive surfaces A and B. Following observation, okay, first, no photoelectric emission takes place. Surface B, photoelectric emission takes place, but photoelectron having zero energy. Okay, so see what is happening here. Yes, radiations of frequency 10 to the power 15 Hz incident on the two photosensitive surfaces. So there are two photosensitive surfaces with name A and B, and here the two signals, two radiations of frequency nu equals to 10 to the power 15 Hz, and here also it is equals to nu equals to 10 to the power 15 Hz. Now, what is happening there? First from the surface A, no photoelectric emission takes place. Okay, definitely. So no photoelectric emission takes place means here the requirement of threshold frequency is greater than 10 to the power 15 Hz. Clear or not clear? Here the requirement of threshold frequency that is greater than 10 to the power 15 Hz. So it cannot fetch out the electron. But here it just fetch out the electron and electron is on the surface means this frequency is only the threshold frequency. So here nu naught is equals to 10 to the power 15 Hz. Clear? Surface B. Explain above observation on the basis of Einstein kinetic energy, Einstein photoelectric equation. How will observation with surface B change when the wavelength of the incident radiation decreases? Okay. For a surface B, what happened when you decrease the wavelength? Check when it is decreased. Okay. So see here, as E equals to h nu, as you decrease the wavelength, so E becomes E equals to h nu means C upon lambda. Okay. So as you decrease the wavelength, this means this whole term will be increases as a frequency. So frequency will be increased there. Clear or not? By decreasing the wavelength, because nu equals to C upon lambda, by decreasing the wavelength, frequency will be increases. And if the frequency will be increases, energy of the total radiation will be increases. Okay. So it will be beyond the work function. And by if it is getting maximum energy comparison to with respect to maximum energy, more than the energy, total energy of the radiation is more than work function, then definitely it will having some kinetic energy and it will be moving. Okay, so by having some maximum kinetic energy. Okay, so here the question is that explain this observation on the basis of kinetic Einstein photoelectric equation. So write the Einstein photoelectric equation. By Einstein photoelectric equation, half mv square, half mv square or kinetic energy is equals to h nu minus h nu naught. Clear or not clear? So half mv square equals to h nu minus nu naught. Clear? So for a metallic surface A, there is nu is less than nu naught. Yes, incident radiation is lesser than nu naught. Clear or not clear? So when nu is less than nu naught, your kinetic energy is equals to negative. This is maximum kinetic energy that will be negative. That is practically not possible. Okay. So no emission will takes place. Clear or not clear? For second case, half Ke max. Sorry. K half mv square, half mv square equals to h nu minus nu naught. In the second case, we seen that nu equals to nu naught. Okay. Or otherwise, you can say the electron was fetched out, but it is just outside the surface without of any motion, means kinetic energy provided equal to 0 equals to h nu minus nu naught. Clear? So taking h downside, it becomes 0 equals to nu minus nu naught. By solving this, you will have nu equals to nu naught. Clear? So the frequency equals to threshold frequency, the incident frequency equal to threshold frequency. Yes, so let us read. Einstein photoelectric equation K max equals to h nu minus nu naught. For a surface A, no photo emission takes place. Why? Because this frequency, incident frequency, is lesser than nu naught. Yes, nu is less than nu naught. Incident frequency is less than the threshold frequency because K max can never be negatives, so there will be no photoelectric emission takes place. For the second case, as there is kinetic energy becomes 0, so nu minus nu naught equals to 0. This means nu equals to nu naught. Clear? Hmm. Hence, frequency of the incident light is equal to the threshold frequency of the incident light equals to the threshold frequency of the photosensitive material with the decrease of wavelength of the light. Yeah, third question started from here. With the decrease of the wavelength of incident beam, frequency increases. Hence, kinetic energy of the incident photon increases. In turn, increases the maximum kinetic energy given by the photosensitive material. Means lambda decreases, this nu increases. So, as an impact of that, kinetic energy also increases. Clear or not? Yes, done. Now, students, important graphs. Some of them we already have covered. So first important graph between the graph of photoelectric effect. First is frequency and stopping potential. So what we have learned that frequency is directly proportional to stopping potential, or stopping potential is directly proportional to frequency. We already have derived this equation. V naught equals to H naught upon E nu minus phi naught upon E. So if you relate, V naught is directly proportional to nu. Clear? Therefore, V naught graph means frequency stopping potential graph is a straight line. Why? Because it is directly V naught with the incident radiation with power 1. And where there is power 1, there is a graph like straight line. Clear? So we already have made this graph here. Yes, see, by the increasing incidence frequency, stopping potential also increases, and this is threshold frequency. And this cut point is what? This is minus phi upon E. Clear? Hmm. So comparing the above relation with y equal to mx plus c, we note that the slope of the v naught graph equals to h upon E. The x-intercept is v naught, and y-intercept is the x-intercept equals to nu naught, and the y-intercept equals to minus of phi naught upon E. Yes. So relationship, if you increase the frequency, then stopping potential also increases. So there is a straight line relationship. Clear? If you increase the frequency, the stopping potential also increases. This is first threshold frequency V naught A, second threshold frequency V naught B, and third threshold frequency V naught for a metal C. Clear? Above the threshold frequency, if you increase the frequency of radiation, then stopping potential increases. Clear? Yes, frequency nu and stopping potential graphs, different material will be represented by parallel straight line because the slope for each straight line is h upon E, that is a constant. But the threshold frequency for different material is different. Yes, frequency depending on the material, so they can vary. So they can have different threshold frequency for the three materials A, B, C. Clear? Frequency nu and photoelectric current graph. Yes. Frequency nu and photoelectric current graph. So here is a metal, like this is a sodium metal, and the incident radiation, the threshold, the work function need by this material equals to 330 electron volt. Suppose it is 30 electron volt. Clear? So as you know, phi equals to h nu naught, phi naught equals to H nu naught. Clear? So if H equals to 3, then nu naught, the requirement of nu naught is equals to 10. Clear? Now, what is happening there? The relation between current and frequency. Check here. This is amount of current and this is amount of frequency incidented. Okay. So the minimum need of frequency here equals to, suppose it is 10 hertz. Clear? Till time you have incidented a frequency of 9 hertz. You tell me, does there any electronic emission will be there? No. Because up to 9 hertz, the energy will be 10, 3 9 ja 27, 23 9 ja 27 electron volt. Yes or no? So there is no emission of the photoelectron. Clear? Because the requirement of energy equals to 30 electron volt. Clear? So up to the threshold frequency, there is no ejection of electron. So the value of current will be 0. So check here. This is the value of current. Okay. Here I equals to 0. Okay. Till the ejection. But as you incidented a radiation of frequency 10 hertz, means threshold frequency nu naught, there will be a ejection of electron and current will be rise. Yes or no? There will be rise of current. Say, check, some current is there. Okay. After then, like you have incident of frequency of 11, 11 hertz or 12 hertz or 13 hertz, 13 hertz. Tell me, students, now correct current will be increases or will be remain constant? No, no way. Because if you increase the frequency, this radiation cannot fetch out two electrons. It can only radiate only, it can only eject only one electron. Clear? And current increases when there is more number of electrons. So one radiation of sufficient frequency can eject only one electron. One radiation cannot eject two electrons. So there is no chance to increase the current. Current will be remain same. Okay. Doesn't matter you incident 12 hertz frequency or 1000 hertz frequency. The rest of the energy will be provided to the as a kinetic energy for the fetched electron. Okay. Yes. So check the relation. Before the threshold frequency, the current will be 0, but at just at threshold frequency and more frequencies, there will be the same amount of current. Clear? The graph shows that the photoelectric current is independent. Photoelectric current, yes, is independent on the incident light till intensity remains constant. Done. Clear? Now, relation between the kinetic energy. So, same because K max is equals to EV naught. Okay. K max equals to EV naught. So, in the place of EV naught, you have to put here K max. So, for threshold frequency, kinetic energy becomes 0. But after then, if you increase this kinetic energy, your maximum kinetic energy also increases. Clear? So as K max equals to H nu minus phi naught, so it is equals to K max is directly proportional to V. We already have discussed this graph. Okay. At x equal to at nu equal to 0, this equals to minus phi naught. Next, intensity and stopping potential. So stopping potential related to the frequency. Yes, we seen this one earlier. We have studied that half mv square equals to half mv square equals to E equals to sorry h nu minus nu naught. Clear? Now half mv square equals to ev naught equals to h nu minus nu naught. Half mv square becomes ev naught because in the terms of stopping potential, this kinetic energy converts into the potential energy. Clear? So this is equals to h nu minus h nu naught. So V naught is stopping potential equals to h upon E nu minus h nu naught, that is called phi naught upon E. Clear? So you can also write this as V naught equals to, sometime it can be written as h upon E nu minus phi naught by E. So check here. This is constant. Phi naught work function is constant. Electronic charge is constant. Only variable V naught is directly proportional to incident frequency. Clear? There is no relation between the intensity of light, means stopping potential is independent from the intensity of light. It depends on the frequency, but it is independent of the intensity of light. Clear? If you increasing the intensity of light, the stopping potential will remain same. So this graph shows that the magnitude of the stopping potential is independent of the intensity of the incident radiation till the frequency of the radiation remains constant. Clear? No impact on of the intensity on stopping potential. Next is time and photoelectric current graph. Okay. So till 10 to the power minus 9 second, electron getting out of the surface. Like this is lattice. So it is this much time it is taking to coming out of the surface. So there is slow increment of the current, but as this getting out of the current, there will you will have maximum amount of current. Okay, so till 10 to the power minus 9 second there is some transition take places, but after it is maximum current. Clear? So this is time versus current. Yes, so this time shows that the photoelectric current attain the saturation value in 10 to the power minus 9 second from a start of the radiation falling on the photosensitive material irrespective of the intensity of incident light. Done. Okay, now we are talking about something about photon. So what is photon? Photon is the quanta of light. Quantum of light means the light coming, light come to any point by carrying some energy bundles. These energy bundles, these energy packet, these quantums of energy all called photon. In the case of light signal, these are called photons. The in interaction of radiation with the matter, radiation behave as it made of particle like photons. Each photon having energy E, h nu, E equals to h nu, and equals to hc by lambda. Momentum of the photon, we will later we study. The momentum of the photon is given by P equals to h nu by c, that is equals to h by lambda. Okay. So make their formula P equals to P for photon, momentum for photon equals to h by lambda. Okay. Yes. Make a note there. P equals to h by lambda. Momentum of a photon P equals to h by lambda. Okay. Yes. Next. Irrespective of the intensity of the radiation, all the photon of particular frequency nu or wavelength lambda having same energy, obviously doesn't depending because the energy is independent from the intensity. It is only depending on the frequency. So if they have the same frequency, they will having same energy. Okay, and the same momentum. Yes, because for a same frequency there will be a unique wavelength and same momentum. Clear? Means if nu equals to constant, this means lambda constant. For a constant lambda, there will be energy will be constant, fixed energy and fixed energy and fixed momentum. And P is constant, P for momentum, right there. So if for a fixed frequency, there is fixed wavelength, means fixed energy and fixed moment. Done. By increasing the intensity of the radiation, the given frequency or wavelength on a metal surface, there is only increases the number of photons. Okay, so if you increase the intensity, number of photon increases, so number of ejected electrons will be increases. Okay, so there is only increase the number of photons per unit second falling on the surface, why each photon having the same energy. But you have increased intensity, not frequency, so each of the photon having same energy. Clear? Yes. All the photons emitted from a source of light travel through the space with the same speed is equal to the speed of light. Yes, they having same speed of light. Clear? So momentum of the photon P equals to mass multiply by C, and we will see this will be equals to M into C equals to H upon lambda. Yes, we will derive this later on. Okay, is equals to H upon lambda. The frequency of the photon, which shows a definite energy of color, does not change when photon travels through different medium. Yes, frequency is the property of source. That's why I am saying it's Aadhaar card of a signal. So frequency is independent because it is the property of source. Clear? So it does not depending on the medium. Yes. The velocity of the photon different medium is different, which is due to the change in its wavelength. As we know, lambda is inversely proportional to mu. So lambda may be changed. Okay. So velocity of the photon may be changed by medium to medium. Clear? Photons are not deflected by electric and magnetic field. Hence, photons are electrically neutral. Photons are electrically neutral. Next, the rest mass of the photon equal to 0. And this is given dynamic mass of the photon. Yes, write this one. This is called dynamic mass, but it's not important. No, dynamic mass. Yes, means when the photon is moving. So by the relativity theory, this mass is obtained. M equals to m naught 1 minus v square upon c square. Clear? This is rest mass. Rest mass of the photon equal to 0.